In this video, we'll be going over generic structures. Generic structures allow you to store any type of data within a structure. Trait bounds restrict the type of data the structure can utilize. These trait bounds are also known as generic constraints. Generic structures are useful when creating your own data collections. For example, you could make custom data collections that are only applicable to data that exhibits specific traits. This is nice because you can add functionality specific to your needs and data types, and you don't have to worry about the collection being able to handle data outside the scope of the types you want to be working with. This results in less technical debt as your program expands. You can utilize new data types with existing generic structures, and they can be easily integrated into your existing code. Here's a conceptual example. We could imagine that we have a generic structure that represents a template rendering engine. The structure can encapsulate everything needed to generate templates. We can have template source paths, variable substitution data, and a generic render target. This generic render target could be able to render to files, terminal, image, or even directly as bytes, and that could be streamed over the internet, for example. New render targets can be added anytime just to the implementation of the trait required by the generic structure. No other changes would be needed, and the program will just work and will have a new render target. Let's take a look at the syntax for generic structures. First, we have the struct keyword, followed by the name of the struct, and then angle braces, here and here. Within the angle braces, we have the name of the generic type. We're using T for this example, followed by a colon, and then the traits that are needed by this type. This generic structure has two generics, T and U. They are separated by a comma. We can then utilize these generic types T and U within the structure fields by setting the type of field 1 and field 2 to T and U respectively. We can also use a where clause to specify our trait bounds. In the second syntax, we have the struct keyword followed by the name of the structure, the generic type names T and U, just like in the first example. We then have the where keyword that comes before the curly braces. After the where keyword, we have our generic type name T, generic type name U, our colon, and then the traits that this generic type is constrained by. For both of these syntaxes, the generic type T must implement both trait 1 and trait 2. This is because we have a plus in between them, so the generic type T always implements trait 1 and trait 2. Generic type U only needs to implement trait 3. And for both examples, we have field 1 is going to be a T, which is trait 1 and trait 2, and field 2 is going to be a U, which only has trait 3. Remember that with generics, these T and U generic types are simply placeholders for an actual type, and the actual type will have to implement these traits and these traits. Here's an example of a generic structure. We have a trait named seat, which is representing some type of seat at a venue, a transportation vehicle, or a waiting area, for example. The seat trait has a single function named show, which has no function parameters and will just be used to print out where the seat happens to be located. Our ticket structure is generic over the seat trait. This means we can utilize a structure with any type that implements seat, but no other types may be used with this structure. The struct has one field, location, which is the generic parameter T, which is some type of seat. Before we can utilize the generic structure, we need some types that implement the seat trait. For our example, we have two types of seating, concert seating and airline seating. Both are enums and both have seating specific to their needs, and they also implement the seat trait as we can see down here and down here. I have omitted the definitions of the implementations, but it's just a match expression that prints out an appropriate message for the seat's location. Now that we have a generic structure, a trait, and some types that implement the trait, we can utilize the generic structure in a program. Our traits and our generic structure are here at the top for reference. In our program, we have a regular non-generic function named ticketInfo that accepts a ticket structure as a function parameter. We always need to specify the type of ticket since we're working with a generic structure, and the type for this specific function is an airline seat. So right here, this airline seat, that's going to be the T for our structure. Since airline seat implements the seat trait, we can use it within the structure here. Using this function is straightforward. We just create a new ticket, set the location to an airline seat, and we just call the function with our ticket. There's no special syntax that is needed for this simple case. Note that while the ticket structure here is generic over any seat type, the function that we have here only accepts tickets that are an airline seat type of ticket. To maximize our usage of this function, we can change it to be generic. This modified version of the function has a generic type T, which must implement the seat trait. Our ticket parameter must be a ticket structure, and it can be any type of ticket as long as it implements the seat trait. Usage is the same as before, except now we can utilize it with tickets having different seat types. So in our example, we have both an airline and concert ticket. So we have an airline seat, concert seat. They're both tickets, and they can both be utilized in the ticketInfo function. And if we were to run this program, we would get output that's appropriate for the ticket locations. So we would print out first class for airline and would print front row for concert seat. We know from the previous lecture on generic functions that the ticketInfo function will expand into two separate functions behind the scenes, one that operates on airline seats and one that operates on concert seats. The same thing applies to generic structures as well. As part of the compilation process, we will have two ticket data structures, one that contains an airline seat and one that contains a concert seat. So if we take a look at this after expanding, we end up with two data structures, here and here, and two separate functions, here and here. You can always think of generics as just regular functions and regular structures with a slightly different syntax. The types will simply be substituted as part of the compilation process. Just like generic functions, this detail is something that happens automatically by the compiler, and you never have to worry about the correct versions being utilized. It'll always work properly. However, the implications of this occurring are larger in comparison to generic functions. It may seem intuitive to just take two tickets and put them into a vector for later processing. Since we could just call a function with different tickets, then this just makes sense. Both data types are ticket, as we can see here, and we both know that they implement the seat trait, so putting them both into a vector seems like it shouldn't be a big deal. However, if we do place them into a vector, we will get this error as seen here, and it indicates that we have a mismatched type. This is because the generic structure is actually multiple different non-generic structures. As we see here in the previous slide, we have two completely separate structures. And we cannot place two different types into the same vector using this technique. To recap, generic structures allow storage of arbitrary types. The types may be of any type, or they may be constrained by traits set on the generic structure itself. You cannot mix generic structures in a single collection. Generic structures expand to structures of specific type, and you cannot mix different types within one type of collection. And generic structures have two different syntaxes. We have the regular generic structure syntax, where we have the generic type T and U, and it's all here on one line between two angle braces. And we have the where clause, which allow us to specify the generic types along with the traits that these types are constrained by.